Today's presenter is Professor Neville Fowkes, who is currently a senior lecturer in the Department of Mathematics and Statistics at the University of Western Australia. He is an industrial mathematics modeler who has attended more than 60 mathematics in industry study groups worldwide, including in Indonesia, Portugal, and of course, South Africa. And he's produced a modeling book based on these activities. He's been instrumental in setting up such workshops and has authored a text on mathematical modeling based largely on problems arising out of the industrial mathematics experiences. This book has been used in industrial mathematics courses in Australia, Southeast Asia, and Europe. Today, he will be presenting a seminar titled Boundary Tracing, a technique for producing practically useful exact solutions to boundary value problems. So I'm going to hand over to you now, Prof. Thank you very much for joining us, and please go for it.
Oh, thank you. So lovely to talk to you guys. Johannesburg is sort of a second home for me, and dear friends there, and it's really, really nice to be asked to give this talk. This is some work that was done by two PhD students of mine, former PhD student Michael Anderson and Conway Lee, who's a present PhD student. Looking over, other people looking over their shoulders were Brendan Florio, Michael Matthews, Des Hill, and Andrew Poissons gave a hand with producing the papers. So let me go on to the first slide. I will describe very briefly the idea, and then what I'll do is I'll tell you the history, how this sort of unexpected procedure arose, and then I'll say a little bit about the general theory and then show you some examples. The idea is really a simple idea. Given an exact solution to a PDE, you may have solved a heat equation with certain boundary conditions, certain flux conditions around the outside, and you've got an answer. The question one actually asks is, can you actually change the domain or change the boundary in such a way that you still satisfy the PDE and actually and the boundary conditions, so you end up with new solutions. And your general reaction, or at least my general reaction, would be, look, you got no hope. But the truth of the matter is that you end up with a lot of very interesting results, really, really surprisingly. The second part of the story is, well, it's maybe just a curiosity. Are these things useful? And yes, it turns out remarkably broad range of new domains, and therefore new exact solutions arise. So it turns out it's a really, really a very interesting technique, I think. The original context really came from a DuPont problem. The problem was this: they were producing capacitors. And to produce a capacitor, you take a slab of silica. Now, when I'm talking about a slab, I'm talking about something that's very small, you know, 1 millimeter by 0.5 of a millimeter. And what you do is you dip it in molten metal and then remove it. So over here, you see it's removed. Now, the molten metal actually rises up the outer face and it dips near the corner. And so when you remove this thing, that's what you actually get very often. And you notice this necking in the corner here. Now that's a bit of a disaster because that's evidently a weak point, and so the capacitor is likely to lose its metal. Of course, what you do is you, having done one side of the capacitor like this, you then do the other side, and there you have a capacitor. So DuPont wanted to know, well, look, how can we actually remove that mooning, the process they call mooning, and make a big difference to their industry? My feeling about this was that if you rounded the corners up here, you're going to reduce this effect. And then the question is, well, will that work? Okay, so that's the context. This problem is a surface tension problem, evidently, or a capillarity problem. And such problems are are of great interest in industry because we're often plating either metals, either metal sheets, or we're often painting things. And so really what happens in these cases is that the coating becomes really quite thin near an edge, and particularly thin or near a corner, so that real difficulties actually arise. And this particular problem we're dealing with here, is fundamental to understanding surface tension problems. The fundamental problem arising here is called the wedge problem. Now, this is a wedge. This is a corner, and you see this is a container. And there's liquid there, and there's the wall there, and there's a corner in this container. And you can see in this case, the water actually rises up that corner and flattens out further away. And what actually happens depends very much on the angle of this wedge. This is a right angle here, and as I pointed out, for most materials, wetting materials, the surface rises in the corner. For a flat corner, of course, you end up with a uniform height rise over here, which is good. If in fact you're dealing with a capacitor, then what you have is an external corner or a re-entrant corner. You have water outside this rectangular face. And under those circumstances, as I pointed out, we have mooning, we have a dipping at the corner. And of course, what DuPont wants to do is they'd prefer to have something that looked like this, you know, the metal being flat, horizontal across the capacitor. Can you do that? Well, this problem, as I say, is a fundamental interest, and it has some really unusual results in the sense that depending on the angle in here, you end up with very, very different results. So this is the general problem. This is the way it's framed. I mean, here's the bottom of the tank, so to speak, and there's the wedge in there. So these are the walls here, and there's X and Y. That's the domain we're interested in. That's the angle in the wedge. And as I pointed out, that can actually, you know, we're looking at a case in which that angle changes from either 0 right through to 3 pi. Against the wall, of course, this is the height rise against the wall as a function of X. It's a function of X and Y, of course, but let's just look along Y is equal to 0. Then you can see that the surface is rising, and that contact angle is something we measure. I mean, I'm sure a lot of you guys had the same problem as I had in high school doing surface tension problems, and you measured that angle. And so in fact, if you want to actually solve this problem, then what you do is you formulate it this way. You think of the height rise at each location within this domain D and call that eta. Then there's the Laplace Young equation discovered, presented by Laplace and Young independently in the early 1800s. And you notice this equation here, what is on the left-hand side is sort of a curvature term. It's a horribly nonlinear term in the height rise. And the right-hand side is really a gravitational term. Now that's called the Laplace Young equation. It's notoriously difficult to actually get information about. And the contact condition again contains that horrible expression up there, dotted with the normal to the face here is equal to the cos of gamma, where gamma is the contact angle. Well, what actually happens here, I won't go through the details here, but if this angle in here is small, now I'm not talking about 1 degree, I'm talking about 20, 30, 40 degrees. If it's small, then in fact, the height rise in the corner is infinite. And in Finn's book, which is one of the classic books on surface tension and capillarity, there's a photograph of this. It really does happen. If he had a box, a container, which with an angle in here and one of the faces, and he poured water in, and in fact you see a photograph of the water climbing up the corner. So so infinite results in a sharp corner if the angle is smaller than a critical value. I should point out that we well know that surface tension is, small things matter as far as surface tension is concerned. For example, of course, the water from the ground is carried up the trunk of trees in small vessels, and an enormous amount of water is actually transferred from the ground through to the atmosphere. And so surface tension is really quite a difficult, interesting area in that small things really matter. Well, for a medium range angle, I'm talking here about maybe a right angle sitting in there, then in fact you actually end up with the solution is really well behaved. It's planar. It's the height rise in the corner is finite and it's planar. So it's a really, really simple regular answer. If the angle is larger than 180 degrees, then you can end up with discontinuities in the height on one side of the wedge to the other side of the wedge. And now, a lot of work has been done trying to asymptotically determine results, particularly close to the corner. In fact, we did some more work on this, but classically, there's an enormous amount of work, and we do know behavior, for example, in the small angle case, behaves like something divided by r, where r is distance from the corner, and we've got similar asymptotic results elsewhere. So it's a very, very difficult problem. And remember, what we're interested in is we want to know what's going to happen if you round that corner there. Is that going to affect things? Well, there's a simpler problem. If the displacement eta of the surface is small, relatively small, then this equation, this Laplace Young equation, reduces to Helmholtz equation. And there it is there. I mean, you can scale things out. So the contact condition says that the gradient, the normal component of the gradient is length 1. And that's the equation we deal with for if the displacement is relatively small. In other words, the contact angle is about pi on 2. And that equation we're very familiar with. And in fact, furthermore, if the angle we're dealing with is a right angle, such as I've presented here, and you can see it there, there's one wall, there's the other wall, and we're determining the value of the height rise as a function of x and y, then in this particular case, there is an exact solution, e to the minus x plus e to the minus, well, there's an exact solution for other angles, but this is a really, really simple result in which you actually end up with a boundary layer coming away from both walls. So we've got an exact solution. And in fact, my thought about this was that, look, if we round that corner a bit, then the way to get at that problem is to use a perturbation technique. You wouldn't expect an enormous change. And so you'd use a perturbation technique to get the results. And I actually asked Michael Anderson, you know, as a PhD student, I said, well, look, why don't you have a look at that? I reckon that's going to work. And I thought if we actually looked at this problem here, we then attack the more difficult problems, horribly nonlinear Laplace Young equation. We'd know how to go about it. But in fact, he was a very good student, and he came back a week later without any results. And after 2 weeks, he came back without results. And as I say, a very good student. I wondered whether I misjudged this problem. And in fact, I had. We observed the following. This critical observation, we noticed that in fact, remember the directional derivative perpendicular to these walls has to be, the perpendicular derivative has to be 1. Now, if you look at the corner at x equal to 0, the rate of change of eta along this 45-degree angle is quite large, but the height rise in this corner, the slope is very much larger than 1, it's 2. So grad eta dot n along that curve there, you end up with the directional derivative equal to 2 rather than 1. 2 is greater than 1, and so if we go away from that particular point, we will find a point P in which grad eta dot n is equal to 1. And there it is there, it's log 2 divided by 2, and it's centrally located. And what this means is that we had a small bit of wall there, which I put in there. And then you can satisfy the contact condition at that local point. Okay, it's the symmetric point. We expect the answer to be symmetric. And in fact, so you actually satisfy the contact condition there. And you might expect that once you start at that point, you can move away from that point, ensuring that the contact condition is being satisfied. And it works. You end up with this curve here, you know. This curve comes away from the point P. It doesn't hit the walls. It actually continues and asymptotes to x is equal to 0. The same in the other direction. So we actually end up with a particular solution to corresponding to smoothing. And in fact, the weird thing about it is it's exactly the same solution as we end up, that exact same solution works in this rounded domain. There's our wall around here, you see. So really quite a remarkable result. In fact, we spent a couple of weeks, we doubted all this and we checked it in various ways to check to see, because it seemed senseless, seemed stupid. But we eventually convinced ourselves that this is the result. To come away from that point, that central point, then this is the condition that the flux, the contact condition is satisfied. And you see, this tells us this, the equation of motion gives us the equation of motion of this curve there. It says that dy dx is obtained by solving this an ordinary differential equation. Remember, we know our solution, d dx and d to dy, with a star sitting in there. And so we can solve that equation, and that's what we end up with. We end up with this result here, this smooth traced boundary. I call it a traced boundary. Weirdly enough, however, it's not the only curve along which the contact condition is satisfied. Here's a whole bunch of these things. In fact, you can start at any point along here, satisfy that equation up there, and you actually end up with these curves here. And you can start along here and do the same thing. So you end up with, along any one of these curves, you've got the contact condition satisfied. So it's really weird. You actually end up with millions of these curves along which the contact condition is satisfied. These are all have sharp corners, and so we really wanted something that's smooth, and there's only one of those, and that's this one here. However, if you're a bit clever, the Helmholtz equation is linear, so you can add in a solution to Helmholtz equation with a singularity at the origin, and in this way you can generate a whole bunch of roundings, if you like, about the corner. Now, I'll use this as a point to actually talk about the general theory. This idea that we presented here, the general theory that arises, is really very interesting. The general theory, the general framework for boundary tracing, it works for linear and nonlinear problems, whatever, is the following. We have a particular function which we know, usually obtained by solving a PDE. And then what we do is we have a flux boundary condition, and you notice it's grad eta dot n, that's a flux term, is some function. It can be a function of x and y and eta and the grad of eta. It can be horribly nonlinear, and the interesting cases are horribly nonlinear. And we ask the question, are there curves C along which this condition is going to be satisfied, given that we're dealing with the function eta of x and y? And there it is down there. There's the equation. That's the tracing equation, we call it. Remember, we do have d dx and d dy. They're known functions of x and y. This f thing, we do know the f, and so we can actually integrate that equation. So that's what we can do, but it doesn't tell you much about what's actually happening. So from this point of view, it's better to look at the geometry of the situation. Our flux condition can be thought of as a condition for determining the normal to the curve that we're going to trace that satisfies the boundary condition. So here's my curve C, and I want to find out if that curve C is such that this geometric condition is satisfied. In other words, grad eta, which we've got, and there's my eta is equal to a constant curve down here, and the gradient is normal to that. There it is up there. And I'm saying, well, look, I want to see if there's a curve here with normal n hat, and of course n hat is defined by the curve C, in such a way that I satisfy that geometric constraint up there. And the answer to this is straightforward. I mean, if f happens to be in modulus is greater than the grad of eta, you've got no hope, because cos theta lies between plus and minus 1. So there are three cases. For any point P in the domain, either we have the modulus of f. Remember, we know f, we know grad eta, so we can actually determine this at any point. If that happens to be grad f is, the modulus of f is greater than grad eta at the point, then you can't trace a boundary. You can't satisfy the boundary condition. If mod f is less than grad eta, then that's less than 1. There are two possible values of theta. And so there are two possible curves through such a point in which we locally satisfy the flux condition. If in fact mod f is equal to the modulus of grad eta, then in fact there's a single curve. And that turns out to be a critical situation. We have, this is called a critical point, and it turns out in order to get smooth boundaries, you need to work with critical terminal points. Now, to actually, let's look back at the Helmholtz equation again to see how all this fits in. As I pointed out, there's the non-viable domain, an area where you can't actually trace boundaries is determined by this condition up here, and otherwise we have a viable domain. This should be viable, not non-viable, sorry, there, and we have critical points. So let's look at this particular example. Here's our two walls, you remember. We're concerned with determining the height rise at any point along these, if the base looks like this in this right angle corner. This region up here, the gradient of eta, with that prescribed eta, e to the minus x plus e to the minus y, well, the gradient is too small. There are no possible boundaries up there. In this region down here, and anywhere in that region there are two possible directions in which you can satisfy the boundary condition. You see one there and there's one there. One set of curves comes vertically and one comes horizontally. And in fact, at the particular point that we identified before, we have a critical point, and then we end up with a smooth curve. So we end up with a rounded curve. But the fascinating thing to me is that this symmetric solution, e to the minus x plus e to the minus y, that same solution works for these really asymmetric curves. For example, I can take this line joined up to that line and join it down to that line and then come across the line down here. And that curve, we satisfy the flux condition. Highly unsymmetric domain with exactly the solution, e to the minus x plus e to the minus y. Really an extraordinary result to my mind. And as I say, it really bothered us for quite some time. Well, our real interest is in the Laplace Young equation. So it turns out there is one non-exact solution to the Laplace Young equation. Now, Young produced that solution in 1804. So over 200 years, people haven't come across any more solutions. It's a horrible looking solution. And you see, this is the height rise as a function of distance y along the wall. And that's what the curve looks like. That's what the surface looks like. And that describes it up there. And you can see the eta occurs in there, and you want to find eta as a function of y. So it's a horrible implicit result. But that's what it looks like. And to use this as straightforward, it's sort of a universal curve in the sense that if you want to satisfy a contact condition corresponding to a particular angle in here, you just identify that angle there, and I've called it P1, and that curve down there represents that's the height rise of the liquid. Okay, so the issue arises here. Well, look, can you trace boundaries corresponding to this exact solution? I mean, it's not like e to the minus x plus e to the minus y, so it's not going to be trivial. It's a horrible expression. Can you trace answer? And the truth is, yes, you can. And there are the curves that come up. Here's one curve. It starts down there, it comes up to C, it goes up to B, and this is the wall up here. And you can, the curve, this curve joins smoothly onto the wall, and so you can add your boundary in which you satisfy this condition can go any distance along here and then turn around here. So, and here's the other curves going the other direction. So, but then in fact, what you can do is you can join these damn things together. And in fact, you can slide these curves along the x-axis and you still end up with legitimate boundaries. So here's one particular boundary, A, B, C, D, E, and that's a curve along which this the Laplace Young solution works. I mean, it's quite remarkable to me. So these things can be combined in all sorts of ways. Now, let me just show you a few examples. I mean, here's a traced curve and here's a traced curve there. And here are the curves going back in the other direction. Well, you can join these together to get this thing here. And that's what the answer you look like. You can see the water going up the corners. And in fact, you can look at this and you can say, if these things are small enough, this is really a rough surface. So we have an exact solution corresponding to a rough surface. Now, the headache you had back in high school with measuring contact angle is essentially you have a dirty surface, then boy, your results are ridiculous, you know. So the effect of having a rough surface or a grubby surface is enormous. Now here we have exact results for the height rise in this rough surface. So, so that's one particular result. Here's a couple of other results. You know, here's the water rising up a corner there, and there's a couple of indentations there, and here are a couple of other corners here. That dot curve corresponds to the wall, normal wall position, and so this region down here is the viable domain, and you end up with these sorts of shapes are possible. An enormous number of these things gets a bit tedious, a bit ridiculous after all. But the important thing to notice is that we're dealing with, going back to that rough surface, that's really an interesting result because in fact, it enables you to determine an effective contact condition for this rough surface defined in terms of the size and distribution of these bumps along the surface. And this is it. Where rho is in fact, you can actually show that this result is, this tells you the effective angle given the real contact in front, you know, on the smooth surface, where rho is in fact the actual surface area, you know, with all the indentations compared with the area of the plane surface. And that is called the roughness factor. And this is the result originally found by Wenzel, really quite a celebrated result. So that all fits in really nicely. Well, I've said that there are no exact solutions if you're dealing with corners, but you can get accurate numerical results, which is what Conway did, and to produce results in a corner. Pity you can't get exact solutions and trace on them, but you can trace with these other things and look for smooth curves or curves with actual corners in them, and that's all okay. And Conway did this, and these are the sorts of results that come out. I mean, you need a couple of nice tricks to actually make this work. And I won't go into the details of that, but you know, that really quite nice work. So this is the case we're actually dealing with the capacitor. You see, this is a right angle sitting in here, and this is the external. This is the liquid around a corner of the capacitor, right the way around there, you see. And that was the initial wedge angle. You see, it's 3 pi on pi plus pi over 2, 3 pi on 2, that total angle around here. And that, in fact, these are traced curves. So these are alternative boundaries, for which the same solution works. And there are a whole bunch of them we've written, Conway's produced in there, and you can work out what happens under these circumstances, what the height rise, in fact, of the dipping, the amount of dipping that occurs in the corner, which you remember is a thing we're really interested in. When you do that, this is the result you get. You see this result down here with the 0.35, and T is really eta, but you can see there's the dipping in the corner. And if you look at these rounded corners up here, you can see the shape as you go around the corner from one side to the other side. You can see the corner is blunt, is made blunt, and in fact the height dipping is reduced a bit, but you know, it doesn't work all that well by just actually rounding the corner in this way up here. Well, it doesn't solve the complete problem, but it's interesting. So if we carry further, if you add in roughness, then boy, you get this. You have to put the right roughness in there, and there's a nice way of doing it, which I don't. You need to define the roughness as a function of distance from the corner. You see the corner is rounded here, and it has this roughness. These bulges have different separation. They're closer together near the corner. And this is the result that comes out. So you end up with a horizontal surface here. If you roughen and round the corner, which is really quite, I think, really quite a remarkable result. Very, very nice work. So it's pretty, and I think it's practically useful. I want to now go on to another area because there are many different areas that Michael and Conway looked at, and we've generally looked at, that produce very interesting results. Now, one problem that Conway has been looking at is the following. It's a radiation problem. Now, I should tell you that radiation is really important in terms of heat transfer, particularly in space, because that's the way energy is lost in space. We don't have convection to help the energy get dissipated. And so really radiation studies are really quite important. So here's, if you like, the generic radiation problem. We have heat being produced in here, and it gets conducted through a body, and then it gets radiated out some surface here. And we'd like to know the solution of such problems, and we'd like to know what the effective shape is going to have on the solution. The temperature rises, etc., the heat dissipation, etc. Okay, so what we need to do is to solve the Laplace's equation here together with a flux condition. And you notice, you remember t to the fourth, this t is temperature here, temperature raised to the fourth power, and that's a highly nonlinear heat radiation term. And that means in practice that when you look at the solutions that people have obtained, they really have only obtained one-dimensional solutions. They can't look at two-dimensional. This is all two dimensions at the moment, okay? So in fact, we don't have exact solutions in this particular case, or even it's hard to get approximate solutions. The simplest problem, which is of this type, is this problem up here. This is a one-dimensional problem, which I have at a constant temperature here supplying heat. And in fact, the heat conducts through this material and then gets radiated from this external face. Now that's the simplest problem you can actually put in here. And in fact, the temperature is simply linear in X. Really, really simple result. Okay, so that's the simplest possible solution to such problems. Well, what happens if you boundary trace it? Well, you end up with these results. Here's the temperature. This is where the temperature is T is equal to 1, say, after scaling. Then that same solution works if you have these spikes. And in the way you can put these spikes together in all sorts of which ways. Here we've got different spikes here, and over here a combination of these things. Now all these have that boundary condition satisfied. However, within a radiation framework, these are not solutions, because in fact, this part of the surface up here radiates to this part of the surface down here. So there's self-radiation. So although the problem with the boundary condition and the conduction equation are the exact solutions of that, there's another condition that you cannot have self-radiation or additional terms arise. But if you look at one section up here, this spike up here, slightly curved. In fact, the amount of radiation involved being lost from this spike is really 0.1%. This is and so you can work out what actually happens using this boundary trace thing, and that's exactly what Conway did. And there's our spike there. It radiates sideways, of course, whereas this is, if we have this little plate here, it radiates forward. So the effect of this spike is that, first of all, the surface area is enormous, so the amount of heat being lost is large, and it's actually deflected around the side, and that can be useful. And so this is a very useful result. And I should add that the results, if you look at the shapes that come out of all this, Conway made some calculation, and they're all in the area that is really of interest, the outer space, and actually also on the Earth. So these are very, very successful results. Let me just look at the time here to make sure I'm not going too far. Okay, if we use, I won't go on much longer, if you actually, another possible solution is that corresponding to a point source, a logarithmic solution. And if you do this, you end up with domains. There's a source in the center here, and these are various shapes that actually arise. You've got a circle, and you can join in these straight lines, these wedges at the edge, and you can do this any which way and it works out okay. So you end up with exact solutions. Again, I must point out, exact solutions. If somebody asks you to solve this problem, I mean, boy, I mean, that's a major undertaking. You can do it numerically, but man, that's not the game. Now, if you actually take into account, if you use bifocal solution, so you have a source sink relationship, then in fact you end up with teardrop shapes. So there's heat in here, a constant temperature surface, and radiation from this teardrop shape, and we got the exact solution. Now, these results are so extraordinary that Conway backs up with numerical calculations, and that's sort of, you know, the grid he actually used. And of course, it works. Remarkable results. They're also lenses and whatever. What I'll do now is just, Michael actually did tracing for a lot of the classical equations, and really weird results, interesting results came out. But I just want to point out to one result here. This is for Poissons equation. This is linear, so you have heat input and you know, under steady state conditions, and you have a flux condition around the outside. This is a domain that's generated using this exact solution down here. Remarkable. Look at that thing. The boundary is made up of things that you can join together. I mean, there's a solution corresponding to this funny shape up here, and a solution corresponding to this shape down here, or another solution down. Boundaries can be combined in all sorts of ways, but take them all together. We have a solution with this radiation condition satisfied for this domain, which is broken up into all sorts of bits. We haven't actually made use of this yet, and it's a very, very interesting. Conway and I did a little bit of work on that, but we weren't. The results weren't as interesting as we like. Also, Michael did some more work on really interesting work. I won't spend more time describing this, but these are solutions for Poissons equation, really important of fluid dynamics, and of course steady state heat conduction with circles and straight lines and whatever weird results. So let me just summarize this story. Boundary tracing requires only a known solution of some sort. It can be a PDE that you solve using separation of variables, and then you can generate out of that an enormous number of possible domains. And in particular, it's important that we can deal with nonlinear problems, really, which are of course, much more difficult than the linear ones. The real strength of the technique is that the trace boundaries can be combined. So you can patch these things together to end up with an enormous range of possible domains. And of course, one of the difficulties about this is that you can't, a priori, you can't predict the shape of the boundaries that actually arise. I mean, you can have a little bit of a punt on it, but you can't predict what it's going to actually be. So that's a bit of a disadvantage. But the other thing I point out, you can round corners, introduce corners, mimic surface roughness, etc. All these sorts of things we often want to do with PDs in their own right. So that I'd suggest that we've seen enough examples in which this has been a really, really effective technique that I think it's worthwhile looking at. Okay. I'll leave it at that and take questions.
Thank you so much, Prof, for a wonderful presentation. I'm really pleased to let you know as well that we have several members of the South African Mathematics in Industry Study Group that was held earlier this year. They're present. So I'm really pleased that they've joined us. And yeah, definitely, I'd like to invite our audience now to please come forward with questions or comments. All you need to do is unmute your microphone and I'll be able to see you pop up with a question. And I'm going to stop my video just so you know, so that we can save bandwidth. Enrico, I can't see where you're from. Would you like to just introduce yourself before you ask your question, please?
Hi, so I am from the University of Western Australia, so I'm one of Nev's colleagues, and I'm impressed by the beauty of the talk and the true. I think the topic is incredibly beautiful, so I'm really fascinated by that. I had the question about the effective corner, effective angle. This is the angle of the domain, I suppose, right? When you were speaking about the cosine of gamma equal to rho, the cosine of the effective angle, or vice versa, I don't remember.
Yes, yes.
But is it possible also to detect some kind of effective slope of the solution? Because I was thinking, for instance, in the exponential case, if you have a convex corner, you would expect at the corner a slope which is higher than prescribed, right? You prescribe 1, but you get 2. On the other hand, in concave corners, you would expect somehow the opposite. So am I right? And is it possible
yes,
to get an average of these effects in a rough domain?
Hey, look, Enrico, thank you for your kind remarks. You know that there's a lot that I haven't actually said here. That it turns out that the corners in these trace boundaries have to live within the non-singular domain. In other words, I said that if the wedge angle is less than a certain value and greater than a certain value, you end up with planar solutions. Outside that angle range, you end up with an infinite answer, or discontinuities are possible. So that when the tracing is actually done, one finds that you cannot allow that angle. You have to work with domains in which you don't exceed those critical values. So there's a lot more information. Now there's a lot more that there's a lot more to be thought about in this area. One of the areas which is most interesting, and I think particularly you would maybe be able to make use of, is that these ideas, I think, are really tailor-made for actually proving theorems. Michael did prove a theorem about the Laplace Young equation concerned with the shapes of domains and the possible height rises, which was a very interesting result, basically using tracing techniques for actually making the problem easier, so you can actually make critical statements about the behavior, but that hasn't actually been done. But there's a lot more thought that needs to go into this work. There's also theoretical work which I haven't described. It turns out that you have to be a little bit careful about when you
make the corners accumulate, right? When you generate these new corners, you can make them accumulate, I suppose.
You can let me go back. I'll see if I.
When you were speaking about the rough boundaries, well, for instance,
see there, that angle in there, that angle in there has to be sufficiently acute. It has to live within the mid-angle range in which there's not singular behavior. In other words, that has to lie between something which depends on gamma and the wedge angle. But it's quite a broad range. And also, yeah. So and this thing here, by the way, is really interesting because if you want to you can see that using this traced boundary here, you get an answer which is pretty damn good in terms of if you had a flat surface, sort of somewhere between the top and the bottom, and Conway used that to determine the effective contact angle, and also Michael did too. It's really quite interesting. But yes, the angle there is critical, and these are, yeah. Does that answer your question, Enrico?
Well, I was thinking about the slope of the solution. So the slope of the solution is roughly speaking 1 whenever it meets a smooth part of the boundary. But at corners, you don't really have a normal derivative, right? So that's the reason for which one is able to make the argument work, because the normal derivative at the corner was 2 instead of 1 at some point you were mentioning.
This is the diagram that, that's the geometry locally, that if you
yes,
take...
but even in the slide before you have
and you
the
see there's an angle, there's a theta there, and of course the other possible curve is this one which is symmetric, corresponding to minus theta. So this curve here, and there's another one over here which satisfies the boundary condition. So that's the geometric constraint on it.
Okay, well, we may have to chat in person. I was thinking about the possibility of making the corners accumulate at a given point, and whether or not this produces an effective slope of the solution, which somehow should average between the concave and the convex part of the domain.
Yeah.
Corners produce formally a normal prescription that should be one the opposite of the other, maybe, or something like this.
Yeah. Oh, that's interesting to, we should talk more about that, Enrico. These,
maybe it's just nonsense, but it's a good way to learn something for me.
See, there's in this wall shape here, the corners here, this is, there's an external corner, there's an internal corner, and of course here we're dealing with a wall situation. In the corner, in the actual, the small angle, wedge angle case, you end up with singular behavior, and I haven't shown you the curves corresponding to that. In fact, we just looked at this, the capacitor case, but so you've seen a very incomplete picture of the work that Conway has done on this. No doubt he'll fill us in at some stage.
Thanks a lot.
Hey, thank you.
Thanks very much, Enrico. Great. I'd like to invite the next audience member to come forward with their question or comments.
Diane, if I could ask a question.
Absolutely, Prof. Mason, please go ahead.
It's just a very general question. When we look for similarity solutions to PDEs, we can usually find a transformation that reduces the PDE to an ODE, but it will not satisfy the boundary conditions.
Yes.
You could perhaps solve the problem for boundary conditions that are satisfied by the similarity solution, and then would it be possible then to use similar methods to go to the real boundary conditions from that solution?
Yes, David, an excellent observation. In fact, there's a lot of good work to be done on similarity solutions here, because as you know, you produce many similarity solutions, and often they really, the boundaries or the boundary conditions don't sort of work out. The geometry turns out to be wrong, and you'd like to actually modify it. Well, I've thought with this process, it should be possible to check for traced boundaries, and one might find, something which is closer to what we want in reality. We know the power of similarity solutions, and and show certainly this should be explored. In fact, I believe that that's probably going to be the major application area, because we have these special results, but using them in practice can be a bit of a problem. Yes, it's something we'll look at, and we might even look at together sometime. Yeah.
Okay, thank you, Neville.
Jeff, would you like to come forward with your question or comments?
Okay, thank you. Thank you, Nev, that was great. Perhaps as a compatriot, I can get away with one of those nitpicking, annoying questions rather than a general one. When you're designing capacitors, you need to know the aspect ratio, length to width, keep them rectilinear in order to predict their behavior. You change the aspect ratio, you change from being rectilinear, you change their behavior. So accompanying this rounding the corners proposal, presumably there's another little piece, much simpler, trivial piece of mathematics, which is working out the capacitor's behavior from the new shape.
Yes,
I guess that's an observation with an implied, question. Did either of the guys do that?
I'm not sure what they actually did with the capacitors. We started on this, Michael and I, we got diverted by this boundary tracing stuff, and it wasn't until Conway came in and looked at the capacitor again. So it was a period of 5 or 6 years, I think, between one and the other, but good to have it finished. But in terms of the capacitor problem, the curving occurs over a distance of what's called the capillary length, and it depends. And you're right, if the capacitor is of around about the same size as the, when you normally put something in a liquid, you see a curved shape, and it eventually becomes away from the region, it becomes flat, the surface of the liquid, and so that's a capillary length. And if the capacitor is round about that size, then you get interactions between one corner and another corner. If the capacitor is small enough, then in fact you end up with a more complicated problem, which all the corners play a role. The same sort of results that we got, the results that Conway got, were really for a corner, external corner. But yes, the capacitor is generally the shape of the capacitor, as I understand it, is really determined by external considerations. You want a square thing of a certain size. Of course, we now deal with a lot of the things we do with the printed circuits. So similar sort of problems actually arise there. So the question doesn't tend to be, it tends to be how you can modify the shape in some small obvious way to get a useful result. In this case, with capacitor, what you do is you roll the capacitors together and let it brush off the corners, and that's the way it would actually work. You could also do other sorts of things, such as changing, the coating of the capacitor maybe to make the same sort of result go through. But yes, that's not we just scratch on mathematics, Jeff, and hope that the engineers work out those things for us or ask us the appropriate questions.
Nice, good. Thanks, Nev. Thank
you. Good to hear your voice.
Thank you very much, Jeff. All right, everyone. So I think we'll wrap up there. Once again, Prof, thank you so very much for presenting with us today. It was absolutely fantastic to have you. You're quite well known to the centre, so to have you present is great, and especially, being an international guest, we're really, really appreciative of it. So thank you very much.